Alrighty, so I think we have everything we need for this. Alright, welcome back to Hardware Design. So I am John. I'm sorry we missed last week. We're in finals week and push came to shove. I needed to kind of work on class a little bit. Interesting, it's rendering blue. Sorry, I'm looking at the monitor and it's rendering something that is normally red and blue. So I just won't worry about that. So where we left off last time was that we have the bounding box iterator, and we need to write a Python script that generates random triangles. So last time what we were doing is we were kind of throwing in snippets of Python and then trying to figure out how to optimize it. And what we were working on were code snippets in the Python, and what we're going to do is take the code snippets to build our quick and dirty verification script. And the way, so let's see. So where we were at last time was we said, okay, well, we have a way to generate random triangles. This is actually 3 times 2. And then we said, well, we figured out at some point is that we don't actually want to have, we don't actually want to keep them in int. We want to have them as float for a little bit. It looks like we need to do some storing on the triangles. So probably before that we'll need to do some conversion, right? We'll need to go, a fix is equal to np dot array of a times 2 to the, I'm sure we said something like 10, 22, because I think this is going to give us numbers between 0 and 1. So now we have numbers between 0 and 2 to the 22, and then np.dtype, dtype equals np.int. So let's make this a bit smaller, because we're going to try copying and pasting the snippets in. Boo. There we go. So A is a triangle now. So we got 3 X and Y's. Now we have decimals that we can output. So we need to go into this line and change the A to A under fix. So now it should just dump. Yep, so we have commas for X and Y, space, so now we have our tuples, good. So now what we need to do is we're going to build the bounding box. So now we have the floating point version of the bounding box. So what we want to do is we want to clamp the first. So let's see, I think min is the first one, yeah. So this is the smaller, this is the outer. So what we're going to do is we're going to want to do some transformations. So the first thing we're going to do is that we want to clamp to, I think we said 8 bits. What is it, 14 plus 8 is where the 22 comes from. So there's 14 integer, 8 bits of fraction. So we actually want to multiply by that, 2 to the 14. So we'll mark that that's screen space, and that's just b times 2 to the 14. So we're going to use SS to keep track of screen space. Good, so now we have something that looks like it's coming out of screen space. And we could be a little bit more clever in how we generate these so that they are all smaller. So what we actually want to do is generate a pixel center, then generate around that in a small radius. All right. So now we have big screen space things, so we're gonna write so now we need so we're gonna say something like, and since we're doing b clamp, screen space is np.array of np.floor of b under ss0. So we actually, this one is seal. Then we want np.floor of b under ss1. Good. Good, good, good. Boo. Ah, too many equals. Okay. So let's go clean this snippet up and then try copying and pasting. Data type not understood. Did we get So the way I debug this is, okay. So I think what's going on is we're missing a set of parens. Yeah. Because this should be wrapped like that. So I think the issue was it was thinking that it was our second argument. Good. So now we have that. So now we have something clamped. So what we can do is we can write np.dtype equals, sorry, dtype equals np.int. Good. So now we have that. And so now we want to add these guys to the string. So let's see if it'll let us do this. S plus equals. Great. So now, and I guess we'd help ourselves out by having a space here between these. Great, great, great. So we're just, right now what I'm doing is I'm just punching it all back in to make sure that it produces the pretty things that we were hoping it does. And then in a second what we'll do is we will start to write a script using these snippets. So if for those of you who haven't done a whole lot of MATLAB, this is sort of the fastest way to write MATLAB scripts. Is you use the interactive terminal to figure things out. What I'm doing is I'm using Python as MATLAB to kind of help me solve problems. So that 6:15 alarm again. So yeah, this is kind of the fastest way to write code, because what I often find when you just kind of write straight code for Python, especially if you're kind of doing syntax you're not super familiar with, so I'm not as familiar with NumPy as I would like to be in any given moment, especially if I'm kind of doing interesting transformations to get text. It requires a little bit of work. Okay, so the next thing we want to do is we want to produce the pixels that are fully contained in that box. So let's see. So I think there's something called np.grid. NumPy grid. Mesh grid, okay. So right now I'm Googling what to do. Return coordinate matrices from coordinate vectors. Make an ND coordinate array for vectorized. So what is this? This is going to be something like np.meshgrid. So let's type some samples in so that we don't end up with something crazy. So let's say I'm asking for a 3x4, and then let's see. We'll offset it by that. Okay, that was not what I was expecting. Okay, so this is really np.range 3, np.range 4. I guess it's a range. returns x1, x2. So what does this return? So what I'm hoping is that there's a command that just automatically outputs what I'm wanting. I do not think this is what I was hoping. Cool. So let's try something else. So there's np.mgrid. That appears to take fun arguments. So let's say we'll do that. So that's looking hopeful. That is indeed looking good. I mean, I want it to go the other way because I really want but you know, this is certainly serviceable. We could write something to swizzle this. So right now, I'm trying to think if this is the most reasonable thing to do. Certainly seems like it. Okay. Because now what we're going to need to do. So this is the widget that's going to make all of the pixels in our box. And so we need to do the little bit of, you know, algebra to figure out exactly what we want. So maybe this is a good time to write simpler script, write our script now that we know that we want this syntax. And then we'll just move on. All right, so let's see. So we're gonna go to scripts, and let's see, we'll call this gen test under BBox under iterator .py. So which Python 3 so that's the shebang. So you use that to make the script executable directly. So theoretically we could if we mark the file as executable, what it'll do is it'll read the file and then see that that is what I'm asking for, that this is a Python thing, and it'll store the Python thing. So let's see, affix. See, so the nice thing is that we keep careful notes. We can just come back and then kind of just unspool. So we've already done that. And then did it include the 5? It did not. So ours is inclusive, so we should probably start with +1 before we forget. Make sure our caps lock is off. So we have BCSS 1 0. So 1 is the index for the big thing. This is the first axis minus BC under SS 0, 0. All right. So we're going to write that right here. We're going to tone this down a little bit because this will be massive. Later on, we'll fix it up. But I don't want it to produce massive things. Right, and then we can write. Let's make this. This is starting to look tiny. Ah! We'll make it huge. All right. So now that's a reasonable size. So we can say Python 3 scripts gen test. Ah, so we already made a mistake. Import numpy as np. Good. So we ran without errors. What we were interested in the moment was seeing that. So it appears that I am producing random size boxes. Good. Good, good, good. And then numpy is np. Is there like an np.zip? np zeros. Is there a zip width? So I think I think why this exists is in most of the tools you would give this as the x vector, and then this is the y vector, and then it would just plot x and y. But I want the tuples, so we're probably going to need to write a comprehension, which is fun. So what we need to do is we want to take the grid thing we made and we want to turn it into pairs. So numpy or two numpy arrays, two array tuples. Merge two arrays. What? That can't be that easy. Oh, so it's just zip. Okay. And what happens if we zip MG0 with MG1? Alright, so we'll try that. So when in doubt, ask the... Oh. So zip is an iterator. Ah, so that's why that's running so fast. So this takes iterators. So may require some magic. Oh, so that is almost literally what's supposed to happen. So we'll try again. I think we're close. Is this actually what we wanted? So what is Z0? So what is Z0, 1? So okay, good. So this is 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 1, 0, 1, 1. Good. So each of these indexes are the pairs. And so we just want to flatten. So mp.reshape. Let's see. So what we want is something like, so numpy flatten multi-dimensional array. Oh. So Z, okay, Z dot flatten. So close, but no cigar. Help Z dot flatten. So I suspect reshape is probably our best bet. So we could do something like z.shape. And so what we should get is z.reshape. So let's say we say something like 10 by 2. That'd be 25 by 2. Does this make sense? And then we're probably going to need to give the order argument. So let's see, maybe so maybe F does what we want. This looks like what we want. Good. Z.reshape order equals F. Is it capital F? No, lowercase f. And then it is comma 2. The first one is z.shape 0 times z.shape 1. All right, so this is getting complicated. So let's try this. Z. Total size of new array must be unchanged. Boo. So what did I do before that made it work? Let's see, z.shape. Z.shape. 0 is 6. 2 is 6. And I got a 1 here. That's the problem. There we go. And there we go. Cool, cool. Cool. So so now we have a little bit of code that does that, and so now we're just going to try and print it so that it can be parsed in a similar format. So what happens if we just write this guy like this before? And that I've copied this 3 times probably means that we should just make this a subroutine. X tuple, give an A. And then good. And then we've been adding a space afterwards. So we'll just add that for free. Good. So now S becomes X tuple affix. No longer need that. There's that. Need to keep this because we're going to do the new line, but we can just write hex tuple BCSS. Okay, good. So let's see. So this is iterate over bounding box. Good. That's a bad sign. So row. we get that. So then what happens? And just for comparison, no, we should print fix. It's the exact same thing. Ah, so that's our mistake. This should have been Z. Yay, copy paste errors. Good. These numbers look big and scary. Okay, so those are big and scary because we're producing 22 random bit things. Okay. So, wow, that was a lot of work. Though roughly in 45 minutes of Python mucking around, we've built a software representation of our hardware. As we have something that takes triangles, builds a bounding box, clamps them. We did so without having to implement min or max or the seal operations that are normally there, and we didn't implement an iterator. We used a built-in iterator. So part of the, well, there are two reasons to walk through this. So one is we need this to verify this guy. Though I probably could have gotten away with doing a worse job. The chances that something is totally broken are pretty small. The other reason to walk through this is to kind of show you that when you go to implement something and then verify it later, in the process of verifying it, you're probably going to say, hey, wouldn't it be great if I had like a software implementation, and you'll go write a software implementation, and oftentimes that software implementation looks exactly like the hardware. And then it's impossible to verify. And even now, we are sort of, in the territory of possibly treading too closely on the original implementation, right? Is, at a high level, it's the exact same thing. So when we go to verify the actual rasterizer, one of the things we're going to need to do is find a raster implementation that we can steal. So hopefully there is some routine that we can write that'll tell us what the triangle coverage is. And I bet in the plotting tool somewhere there's a built-in rasterizer that we can play around with how it works to get where we're going. All right, so for next time, because I gotta bump out early tonight, finish this script. So one is random small triangles, and two, some number of triangles, maybe an argument. And then implement BBox iterator top to read file and check. So one thing that we need to make sure of, one thing that we didn't fix was that we didn't add the thing. So, add min here so that it's in the right numbers. And then sanity check. So we should just look at a couple implementations and make sure the outputs that it's doing are seem reasonable. Read file. Play stimulus. Populate sample scoreboard. And then pop scoreboard if hit, otherwise throw error. Write some assertions to check the test. Sample in store BBox. Cool. So the reason that we're doing that is that, A, I forget what I'm doing part of the time, and B, it's a good habit to get in, even if you're going to walk away from something for an hour or so. Just kind of write down what the next steps are to make sure that if you're coming back to the code and maybe not the best state of mind, like I haven't slept in a couple of days, and hopefully that wasn't obvious. I didn't. My pinwheel is turning. Even if it's for a few hours, if you come back to something and you're not in the best state of mind, usually it provides you with a good hint about what the next immediate steps are. So in this case, when we get back, we know that we needed to do something with the random small triangles, is that we are generally just going to produce massive triangles. And I don't know about you, but I'm not willing to wait for a million simulation cycles to check bounding boxes. Like, yes, our bounding box should work for large triangles, so maybe we should produce ones of random size with a low probability for large ones. But we shouldn't be doing almost all large triangles because that could take forever. All right. So I hope you all have a nice week. And for those of you who are tuning in during finals week, I hope your finals are going great. And I will catch you all next time. I suspect over the winter break I'll be a little better about doing the vlog, and then I'll probably miss one for travel in late December. And then hopefully next semester I'm doing better on doing one of these every week. Certainly some of the comments I've gotten informally from some folks have been that this is not the most useful hardware design to worry about. So feel free, especially if you're the one or two folks who consistently log in to watch. If there's something you'd rather see me build, let me know and we could change context. There's no actual customer for the rasterizer. This is just something we're doing for fun. So we could switch to a different design if folks were interested in that. They're probably not something that I use in the class. Though maybe that might not be bad, because if somebody's willing to sit and watch all the videos to do the homeworks, all the power to them. But otherwise, have a great night and a good finals week. I will see you all next time for more triangle rasterization.